Testing, testing. Yeah, I'm recording now, so you
I think 11 people in total, 2 online, so what was that? That makes 8, so 3 missing. I guess they'll show up a little later. Well, my name is David Slatter. I'll be your lecturer or teacher for part 4 of your Chartered Financial Analyst or Certified Financial Planner. What is the acronym? CFP, Certified Financial Planner course. And we're going to look more at investment products and markets. And tonight we're going to talk about time value of money. So, time is the key factor, whether it's you borrowed money and the interest you got to pay back, or investments you made and the interest you earn on your investment. And my name is David Slatter. I'm currently the AVP of Investments at Royal Fidelity. Academic background, I'm a chartered financial analyst, and I have an MA in economics. So economics at university, then I did my CFA designation when I got back to the Bahamas. Anybody who can guess which high school I graduated from in St. Augustine's? Which high school I graduated from in Nassau, then you get $10, but I gave it away so nobody gets it. Okay, class of '85, Big Red Machine, proud of it. Here's my email, swimbolds@gmail.com. So any questions you have, that you may feel uncomfortable with here in the class, but you want to ask them, send me an email. No dumb questions. I guarantee you it's in your head since somebody else has said it. All right? If you thought of the question, it may seem simple. You're a little embarrassed about asking it. Don't. Somebody else has got the same question. Okay? And quite often one question leads to second questions and third questions, which are all useful and beneficial. So tonight we're going to look at time value of money. We're going to look at future cash flows or future value for a single payment or future values for multiple periods. We're going to look at the present value for a single period or multiple periods. We're going to look at the discount rate. We're going to look at the number of periods. So we're going to actually calculate the calculations on the discount rate calculations for the number of periods. There are computer programs out there that do this for you, right? But it's important to know from a mathematical standpoint what's being done. I know when I first moved back to the Bahamas, the bank I worked for at that point, I went and did the calculation in Excel on what the correct payment should be on given loans, and my calculation was a little less than what the bank system generated. So their system erred in their favor. So just don't assume the computer or the calculator is doing it correctly. Then we're going to look at annuity payments or present value for annuity cash flows and the future value for annuities, the effective annual rate of return, and then we're just going to talk about some loan types, pretty basic stuff. Okay. This handout I gave you that you received, it's from an Excel spreadsheet. You'll see that I've actually got a number of formulas actually included on it. So these are the formulas for the most part that we're going to be looking at tonight. And the first thing we're looking at is the future value. So let's just go through the notes and go through the example on page 2. So this is a very simple example, nice easy numbers to work with, right? This is why most of the world uses the metric system, and only a few countries, Bahamas and the US, use miles per hour and those kinds of things in pounds instead of kilograms and kilometers. So if you were to invest $1,000 and you're getting 10% return on your investment, how much would you have at the end of 1 year? So it'd be 10% on the 1,000, which is 100. So at the end of the first year, you'd have 1,100. So in this example, it's pretty straightforward, you know. One period, it's simple. When you start to add in multiple periods, then it becomes a little more complicated. So why don't I, at this point, I'm going to write the future value formula on the board, so you're aware of what it looks like. So this is a problem of future value. FD. So future value equals the present value times 1 plus the rate of return raised to the number of periods that we're talking about. Okay? So I think on this, I kind of spell it out on the handout you've got. So FV, future value, PV, good evening, present value, R is the rate of return, and T represents the number of periods over which this investment will occur. So in this case, you know, I've got $1,000. If somebody's going to pay me, or a company's going to pay me 10%, if I lend $1,000 to them, at the end of 1 year, how much should I have? So let's go through the actual steps. Even though it's a simple example, let's go through the steps because it's important. We've got 4 variables, right? We're trying to solve one of them. We've been given 3 of them. So the first thing is write down the information you've been given. So what do we know? We know that the present value equals 1,000. We know that R equals 10%. And we know that T equals 1 in this case. So then we just plug that in. 1,000 times 1.10. Quick refresher, right? 10% equals 0.10 is a decimal, right? 100% equals 1.00. 1% equals 0.01. This is all going to be important, so do a refresher of all the decimals to percentages and percentages to decimals. So 1 plus 10% is 1.10, and that's all raised to the power 1. Anything raised to the power 1 is itself. Okay? So now we have 1,000 times 1.10, which equals 1,100. Okay? So that's really about as simple as it gets. Okay? Now, in this example, we said, what about 2 years? So if I can invest $1,000 at 10% for 2 years, how much will I have at the end of 2 years? Okay, we see here, there's 2 ways you could do it. You can take 1,000 times 1.1, you get 1,100. Then you take 1,100 and multiply by 1.1, and you get 1,210. That extra $10 represents interest on the interest. That's the power of compounding. Or we can use our formula here. Everybody has that? Okay. The only difference now is that T is 2. Okay? 1.1 raised to the power of 2, or 1.1 times 1.1, gives you 1.21. And this gives you 1,210. So the reason it's not 1,200 is because in year 2 you earn 10% on the $100 you earned in year 1. All right, so now you can see how when you start looking 5 years, 10 years, 20, 30 years out, the compounding becomes very material. Okay, and that works well for the investor. It doesn't work very well for the borrower. So if you have a mortgage and you're paying 10% on your mortgage, for example, or you have credit cards and you're paying 18%, that builds up really quickly. All right. So this is a 2-period example. So any questions at this point? The concept of the math, the algebra, you know, variables for different variables, and the fact that we're trying to solve. We have 3 of them. We plug it in and we solve for the unknown. Okay. All right. Let's do a slightly more complicated example, as you see on page 3. And what we'll do is we'll do some other examples along the way, so everybody has a chance to do the calculations, because I'm sure Miguel will make sure you're tested on it, right? Right, Miguel?
Definitely.
All right. So, compounding interest. So in this case, this is page 3. Mr. and Mrs. Smith have a 6-month-old baby. Mrs. Smith has just received a $1,000 bonus. Should they buy some new furniture or invest in security earning 10% per annum? Right, you know, either answer would be reasonable, right? Furniture is going to be, but let's suppose they decide to invest it, because the idea is, you know, in 20 years, our child has to go to university, so we need to start saving for that. So, in this case, let's see, she can earn 10%. I love, you know, very optimistic rate of return, but it's easy at this point for calculation purposes. So the future value of furniture will immediately start losing value, and in 20 years is worthless. But if she were to invest $1,000 in a bond that pays 10%, what would that be worth at the end of 20 years? And you see the answer there is $6,730. But why don't we go through the steps using the same setup we've got here? The only difference now is T is 20, right? Now these are all annual rates of return in annual periods, right? When we start dealing with semi-annual and quarterly and monthly, that becomes a little trickier, right? Because the number of periods goes up, then the interest rate has to be a monthly rate, or a quarterly rate, or a semi-annual rate. So this is raised to the power of 20. Everybody has their calculator? All right. And we know how to do the exponential? Calculator's on there somewhere. I open it. Run that along. I got my money's worth of this calculator, that's for sure. This is from 2002. I started the CFA program. So, changed the battery a couple times, still works. So, the symbol is y to the x. You see that in your... So all you do is you go 1.1, then you hit the y to the x, you hit 20, and equal, and you get 6.73. Okay? So that figure, that 6.73 is called your future value factor. Okay? 6.73. Now, of course, you know, you can go out, I'm sure in decimals, I don't know if it goes out further or not. Yeah, 6.7275, go out to infinity, I'm sure. But for our purposes, this is good enough, 2 decimal places. So 6.73 times 1,000, 6,730. Okay? And that's just for making one investment. Later on, what we're going to find out is, well, what happens if I say, if I make a $1,000 investment every year for 20 years at 10%, what do I have? And that's a more realistic scenario, right? Talk about investing, putting money aside every month. And what you're going to find is this. I want to make sure Miguel gives you the Excel of these, because this is pretty cool. This is, you know, it's not that complicated, but it allows you to plug in assumptions, right? Assume rate of return, assume number of periods, initial investment. What am I starting with? 0? Am I starting with 50,000? What am I starting with? And how much do I have to put in every month or every quarter, or whatever, determined to get to my goal? Because quite often in the investment world, people will say, well, I'm 30, I'm going to retire in 35 years. How much do I need to retire? Well, that's the first question, right? Do I need $1 million? Let's assume we need $1 million. How do I get to $1 million from today? And this helps you with giving them some guidance. Do you need to save $1,000 a month? $2,000 a month? Then reality sets in, right? Well, I can't. Where am I going to get $2,000 a month from? All right. Then you look at the budget and on, and you dig down and go, do you need a Coca-Cola every day? Do you need to buy lunch? Do you take lunch? Where do you find that money from? That's really a financial planning question. So, this is a situation, one single payment, 20 years, 10% After 20 years, she's got $6,730. Okay. What are some of the risks that may not occur? Just out of curiosity. So, in this scenario, we say she invested in a bond, right? In a security. What are some of the risks related to securities? Yeah, the price could go down. The company that issued the security could go bankrupt. And therefore, you lose your $1,000 and the interest that was owed at that point. That happens, right? That's why it's important to understand the risk associated with the investment as well. Okay. And in today's market, if somebody comes and says, I got an investment that's going to earn you a 10% rate of interest, run for the hills. That's risky as can be. All right, the only way you get a 10%, you know, unless you're a bank, then you get away with it, right? All right. So what next? What are we going to look at next? Let's look at calculating the present values. Now we're going in the reverse. Okay. So that could be. Let's suppose, you know, we'll go through this example, but let's suppose that somebody says, you know, I'm going to give you $1 million in a year from now. All right. But you're trying to determine what that's worth today. All right. So the present value of $1 million a year out, or the present value of $1 million 10 years out. So that's what we're trying to calculate now. So I'm going to erase this, and we are going to do a little algebra. So now instead of solving for future value, we need to solve for present value. So what's the process to do that from a mathematical standpoint? How do I rearrange this equation so that I have a present value all by itself? That's right, because this is really a single variable. All right? Don't get caught up by the 1 and the r and the t. It's 1, it could be b. I can define, you know, b equals 1 plus r. Right? So you're absolutely right. We divide both sides of the equation by this. So we divide that by 1 plus r to the t. We divide that by 1 plus r to the t. These cancel out. And what we're left with is present value equals that. So we just flip it around. Present value equals future value divided by 1 plus r to the t. All right. And this is the same as future value over 1 times 1 over 1 plus r to the t. All right. So that's the same as that. Okay. So that, you know, they're the same, right? The only reason I do that is because now this figure here, or this value here, is what we call our present value factor. So quite often you can calculate that independently instead of going through all this, and just you simply have that already. Divide future value by your present value factor to get present value. All right. Okay. We were going there. All right. So I'm going to erase this and just put the present value formula up so we can do this calculation. Is this far enough to the side for everybody to see? Miguel's not going to make you do those mathematical calculations. All right. So if you just memorize present value equals future value divided by, that'll work too. All right. So he's not going to say, here's future value, do the algebra to come up with present value. You're not going to have that kind of question. This is a financial planning course, not a math course. Algebra. But there is some math. So present value equals future value divided by 1 plus r to the t. All right. So you can see present value is going to be less than future value, right? Okay. Because this is greater than 1. Something divided by greater than 1 is, it goes down in value, right? So what is our example? All right. So when we discuss future value, we're thinking of questions such as, what will my $1,000 investment grow to if it earns 6% every year for the next 5 years? The answer to this question is what is called the future value, and it happens to be 1,338. Another type of question that comes up even more often in financial management is obviously related to future value. Suppose you need 10,000 in 10 years and you can earn 6% on your investment. How much do I have to invest today? And this would be a single period case, right? So what do we know? We know that future value equals 10,000. We know that R is 6%. Yeah. The rate of return is 6%. And T, what do you say? 10 years, right? So we just plug in these values divided by 1.06 raised to the power of 10. All right, 6% divided by 100. Eliminate the percentage sign, right? That's how you get the decimal. Okay. All right. 6% divided by 100. We get rid of that. Equals 0.06. So 1.06 raised to the power of 10. We get out our calculator. We go 1.06 yx 10 equals 1.79. This equals 10,000 divided by 1.79. Now, another little trick, right?
Do that for me slow again, please. When they left high school, they haven't done this. I'm serious.
Well, like I got an A in GC math, and I went to university, they put me in pre-calc. I said, what is calc? You didn't even do calculus when I was in high school. That was the British system too. Nowadays, the kids are doing calculus in grade 10. The 1.06 raised to the 10?
Yes.
Okay. On the calculator?
Mm-hmm.
All right. 1.06. Then you should have a symbol there that says y with the x exponential.
I got that one, yeah.
Press that. And then hit 10. Add, enter 10, because that's the number of periods. Hit equal, and you should get 1.79.
Okay.
Now, because you're dividing, right? You know, you could go 1 divided by 1.79 equals, and then multiply that by, well, you can do 10,000 divided by 1.79. That's easy. That's easy way to do it. Yeah. But no, sorry. You got 1.79 on your calculator. You got to clear that. You need to write that down and make a note of it, or remember it in your head. Then put in 10,000 divided by 1.79. There's opportunities to make mistakes, right? You think you remembered it, you put 1.79 and 1.97 instead of 1.79, or you write down the wrong number. You're stressed, right? What you can do is hit the inverse button, 1 over x, on your calculator. Do you see that? So if you have 1.79 in your calculator right now, there's a little button with 1 over x. You hit that. 0.56. Then you multiply the 10,000 by that. And you get 5,583.95. Right? So just a little step saves time, and it eliminates risk of making a mistake.
How do I reset my calculator? Because I'm getting 5,586.
Okay. Just hit clear. Use the CE or.
Yes, I get that. I mean,
Who's
the
that?
actual setting.
I see.
How do I do that? I have two decimals. And this, but I know what I'm wrong with that.
Let's try it again.
Okay.
So 1.06 raised to the power of 10. And what do you get at that point?
Let me do that. 1.06.
Raised to the power of 10.
6.05 e negative 13.
Ooh, okay, something's going.
Something's going on. I can't use this.
Not that I'll know what the heck I'm looking at here, but let's clear it. 1.06. simplified, it's just cutting it off. Whereas, like my calculator shows 0.56, but it could be 0.5, and it looks like it's just stopping at 0.56. So, as a result, you probably get a value a little less. 5,583.95. Yeah, so always, just make sure you hit the clear.
I'm gonna try it again.
Try it again.
Thank you.
All right. So let's look at single period case, all right? So present value times 1.1 or 10% equals $1. So we're saying a year from now you're going to have $1. What do you need to invest today at 10%? All right. So it's a simple version of what we just did. So future value is $1. R is 10. T is 1. One. All right. 1.1 raised to power 1 equals itself. Inverse is 0.91 times 1. 0.91. I think here I had 0.909. We went out 3 decimal places. Equals 0.91. Now, this 1 year present value calculation is important investment because when you're dealing with treasury notes or T-bond, treasury notes, they have maturities 90 days, 180 days, 360 days. And they are a zero coupon bond in effect. You buy them at a discount, and at maturity they go to their par value. So for example, $1 million of, and a lot of central bank is issuing treasury bills all the time, right? A lot of banks invest in them. So they say, $1 million 1 year treasury note. Today we're selling it for at a discount, and whatever that discount will be based on the rate of return that's built into it. So the 2% rate of return, what would the present value of $1 million be? Right? So we can do that quick calculation. So the future value is $1 million. The rate of return is 2%, and T is 1. Two raised to the power 1, so 1 million divided by 1.02. My bad handwriting, I blame on my parents because I'm left-handed. It's not my fault. So what do? We take 1.02, take the inverse of that. We don't have to multiply by 1, but raise it by 1. Inverse of that, 0.98 times 1 million. And we get 392.16. All right. What, in this case, you'll have to give the central bank $980,392.16 today, and 1 year from now you get $1 million. Okay, so that's called a zero coupon bond. There's no interest payment. It's simply you buy it at a discount, and at maturity you get the full value. Okay. All right. What about the present value for multiple periods? Okay, so suppose you need to have $1,000 in 2 years. If you can earn 8%, how much do you have to invest to make sure that you have $1,000 when you need it? In other words, what is the present value of $1,000 in 2 years if the relevant rate is 8%? All right. So we know the future future value is 1,000. We know the rate of return is 8%. We know the period is 2 years. In this case, 2 years. The period is 2. Today's class has the most math. All right, much less math in the next 2 classes. Okay? Or less. All right, so future value is 1,000. The rate of return is 8%, and the period is 2. Future value of 1,000. Present value is that 1.08 raised to the power of 2. Calculation. Take 1.08. Raise the yx, raise to the power of 2 equals 1.17. Take the inverse of that, we get 0.86. We multiply 1,000 by that, and we get 857.34. So, if we need, if we want $1,000 in 2 years and we can earn 8% on our money, we need to put $857.34 in that investment today. Okay? You know, if you go into a bank and they're going to give you 1% on your fixed deposit, and you need $1,000 in 2 years, it's going to be pretty close to $1,000 you put in today. A little less, but not much. Okay? And you know, this kind of scenario, somebody comes to you and says, you know, I'm going to retire in 20 years. I think I need $1 million to retire. How do I get that? You can do one calculation and say, well, if you had $100,000 today and you invested it for 20 years at 5%, what would you have? All right, you can see what it turns into, right? And see if they're falling short or they're ahead of what they need, their target. In 5 years from now, I'd like to buy a lot of land for $100,000. How much do I need to invest every single month over the next 5 years so I can have the $100,000 to buy a piece of land? My car is getting a bit old. I think I've got about 3 more years of life in it. I'm going to need to buy a new car in 3 years, right? I don't want to pay. I want to at least have $10,000 to go towards it. What do I have to save every month for the next 3 years to get to $10,000? My children are going to go to university in 10 years. University costs a lot. You figure out what that amount is. What do I need to save every month over the next 10 years to get to that target? So these are very, very real day, everyday questions, right? What do I need to do today to get to a target in the future? All right. Sometimes a bit depressing when you actually calculate the numbers. You go, all right. Plan B. Teach at the Bahamas Institute of Financial Services. This is a part of the class, but let's talk about, you know, say a loan or mortgages, right? Quick graph. The thing is always useful. It is relevant, right? Because in this case, you are borrowing money from the lender. They're charging a rate of interest over a period of time. Ideally, they'd like you to simply make nice, same payment they've contract you've agreed to. Make that payment every year for 20 years, pay that payment every year for 30 years, because it's in their interest to earn interest, as much interest as possible. So, if this is time. I got it anyway. And this is the mortgage principal, right? Let's just suppose this is 100%. The day one you borrowed it, that's 100%. That's how much principal you owe. As you're making your monthly payments, it's amortizing over the life of the loan. Let's suppose this is 30 years. The principal barely goes down, right? Barely. As you get further and closer to the maturity, then the principal really falls off quickly. So in day one, almost all of your payment is interest, very little principal. And as you get out here, more and more of your payment is principal and less is interest. Okay? So how do you change the shape of that graph? Add a little extra every month. $50, $100, and you're surprised. You suddenly take a 30-year mortgage and you can turn it into, 25, 22, 20-year mortgage, right? Depending on how much you add to it. And what does this represent? That's interest that you did not pay. That's interest the bank did not earn. That's interest you didn't have to pay. All right. You add all that up over a 30-year mortgage. That's paying money. Okay. And then, so you paid off your mortgage earlier than they thought, or now you've got this period of time where that mortgage payment you're making, if you're disciplined enough, keep invested. Keep it's in your budget. You're not spending it. Put it in something. So now, at the end of 30 years, instead of just paying off your mortgage, you now paid off your mortgage and you've got an investment. Okay? And remember now, if you've got a debt, the rate of interest on that debt, every time you pay down the principal, that's in effect the rate of return you're getting on that money. Because if I didn't have to pay 10%, I save 10%. So it's really a 10% risk-free rate of return. There's no risk. My principal went down, I didn't have to pay interest of 10% on that principal. I'm going to rate my pocket, and there's no risk, obviously. All right. Okay, credit cards, if you can, pay them off at the end of the month. I know, easier said than done, right? But imagine 18%. All right, what are we on? Which question are we on? We did that one. Let's do calculating the discount rate and the number of periods. All right, this when I give you this, when you get this spreadsheet, this will allow you to play with numbers and you can actually tweak the numbers and get that result. All right, we're going to do it the painful way. We're going to do the mathematics behind it today. All right, so. We got our, here we show you the future value factor that I mentioned earlier, 1 plus r raised to the power of p. The present value factor is 1 divided by 1 plus r to the p. And the question is, all right, in fact, the easy way to calculate the present value factor, well, we did that already, do the inverse, okay. We've actually covered that bit. So let's look at determining the discount rate. So frequently we need to determine what discount rate is implicit in an investment. We can do this by looking at the basic present value equation. We'll go to the next page. All right. So in this case, we're trying to solve for R, right? Okay. The first thing we're going to look at is the rule of 72. Okay, the rule of 72 is a back of the envelope formula you can keep in your mind. So the question is, how long will it take an investment to double in value? So if I have 50,000, how long will it take 50,000 to become 100,000? You take 72 and divide it by the percentage, the return you can get. All right. So if you can get 7.2%. 72 divided by 7.2 is 10. So your investment will double in 10 years. If you can get 3.6, 72 divided by 3.6 is 20. 20 years for your investment to double. So it gives you a kind of a rule of thumb. If you can get 7% rate of return, then your investment will double in approximately 10 years. So it's not meant, the rule of 72 is not meant to be it's meant to be an estimation. All right, and it's useful. So if I can get, well, obviously if I can get, we just take 72 and divide by it. So you can get 5% rate of return, 72 divided by 5. Forget about the percent, eh? Just use the 5. 14.4 years. So it gives you an estimate of how long it will take an investment to double in value. Okay. So also, how long will it take the debt I owe this entity to double? So I got a credit card and I'm paying 18%. 72 divided by 18. 4 years. So that $5,000 you owe turns into $10,000 in 4 years. Because of the 18% interest being added to it. Assuming you're allowed to go up to that to give you an idea, compounding is really good when you're earning it and really bad when you're paying it. All right, so now we're going to do the calculation to determine the rate of interest. It's not here in the notes. We'll do it on the board, and then you can write it down in the notes. Let's start with the future value equation. We're trying to get R, right? So the first thing we're going to do is isolate this bit here. We divide both sides by EBT, present value. We cancel out. Now we've got future value T. T. All right. Now, how do you get an exponential down so it's an integer or a normal number? You can take the log, the natural log. You can take the log of that. Pretty sure he's not going to make you do this on the test. Huh? I hope not. Well, let's do it anyway. And you have an ln on your calculator, right? So if you look, you'll see a symbol ln. See that on your calculator? So future value equals 1,000. Yeah, all right. Present value equals 900. And T equals 2. You need to know what R is. Well, we've gone to this point. We know what future value is. We know what present value is. We know what T is. We're just trying to solve for R. So we plug everything in. The natural log of 1,000 over 900 equals 2 times 1 plus R. Yeah, you said I'll make you do this on this. I think that's just having fun one. That's what we're doing. Make people mad at me. All right. So, and you can't see because I'm in the way. So let's determine that 1,000 divided by 900 equals 1.11. Take the natural log of that. And we get 0.11 equals 2 times 1 plus R. Divide both sides by 2. And we get 0.055 equals 1 plus R. Therefore, R equals that doesn't make sense.
Why would you divide them by 2?
I was trying to get rid of this 2 here. Let's regroup. Now we have the natural log of right, guys, I'm gonna have to regroup. Do this calculation. When you do what did you get when you do 900 divided, 1,000 divided by 900, and then take the natural log? What did you get?
I get something that was
0.11?
105.
105.
It's still up in there. That just means don't do that. Whatever that is.
Yeah. All right, I'll regroup. I'll come back to you on that one. Oh, all right. I know what it is. This equals not t times 1 plus r. It equals t times the log of 1 plus r. Okay. All right. So we come up here, and we've now got, we know that it's 0.11 times 2 times the natural log of 1 plus r. We divide both sides by 2, 0.055 equals the natural log of 1 plus r. What's the reverse of log? It's exponential. All right, so if I take the exponential of this, thought I had it figured out. Let's see. I'll come back to that. It's not wasting more time on that. But the trick is, yeah, I eliminated the natural log when I did the exponential value. Keep that in there. All right.
You eliminated T earlier because it was redundant. And FVT over PVT is T redundant, that's why you took it out?
Well, these are just, it's not actually a it's just a notation. It's just saying future value at time t. So it's not, it's not, you're not multiplying by t.
Okay.
So I mean, you could have taken that with it. All right. Why isn't it working, man? It's supposed to work.
So it's supposed to be the natural log of FD over PV is equal to the natural log of.
The natural log of FD over PV equals t times the natural log of 1 plus r.
Of T times the natural log of 1 plus r.
Right.
Mm-hmm.
Divide by 2. No, that's what I did. I divided both sides by 2. We can figure it out, you know. I mean, if it was 10%, 1.1 raised to the power 2 times 900 is more than 1,000, so it's less than 10.
Why are you dividing both sides?
It's a little over 5%.
So when you cross that over, you divide into 2, right? You take the 2 over on the other side.
If I divide by 2 on both sides?
No, one side over here.
Well, to get rid of the 2, I have to divide both sides by 2.
Why?
Because when you do the one side of the equation, you have to do
But you say that's a multiplication on this side.
yeah, 2 times.
But if you move the 2 over the equal sign, doesn't it just automatically divide?
Well, to get rid of the 2, I have to divide this side by 2. If I divide this side by 2, I have to divide that side by 2.
No, I mean just divide one side, the side over here, because you're moving the 2.
Well, I'm trying to eliminate the 2. The only way to eliminate is
He had the
divide.
step, but in algebra, we didn't learn it like that. He had the step as to why we can cross over.
Right, right, he's showing.
And the crossing over, that's essentially what you're doing when you cross
Oh,
over for algebra.
you're doing the next
Yeah,
side.
you have to do the same thing on both sides. We didn't learn that step. We just cross over.
I've
We
done
didn't do the opposite. That's what we were doing.
I've done a great job of confusing, but I'm doing it myself. What does the sum assuming do? Assuming I remember how to do it. Not of you, but it made it of me. That's a good one, you gotta remember that. But I assume, you know what assuming does? Made us both look silly. All right, now, seeing that I've got all the calculations here on the paper, I'm pretty sure we can do the next one. But you know what? Just look at that. I mean, this is even nastier than what we were trying to do before, right? In this case, we're trying to solve for t. Wait, here we're solving for r last time. This time it's t, and it goes through a lot of the similar steps, right? Where you have 1.1 raised to the power of t equals 2. You take the natural log of both sides. You get the t down. So the natural log of 1.1 raised to the power of t equals t times the natural log of 1.1 equals the natural log of 2. Therefore, t equals the natural log of 2 divided by the natural log of 1.1. The natural log of 2 equals 0.6931. The natural log of 1.1 equals 0.0953. You get 7.27 years. And this is basically doing the calculation of the rule of 72 that we talked about, right? So if you're getting in this case, it went from 50,000 to 100,000. The rate of return was 10%. So T, using the rule of 72, was going to be 7.2 years. If you do the actual calculation, it's 7.27 years. So it's pretty close. It's a very good estimate, but it's not exact. Okay. There's no way. I'll double check with Miguel, but I don't see you being tested on that particular calculation. That's nasty, right? All right. So now let's look at future value with multiple cash flows. Okay, so much like a, you buy a bond, right? You buy a bond and it promises to pay an interest payment every 6 months or every year, and you get principal back at the end of the maturity. In total, what do you get? What are all your cash flows when you add them all up? So in this example, suppose you deposit $1,000 that's paying an account earning 7%. In 1 year, you'll deposit another 1,000. How much will you have at the end of 2 years? This particular problem is relatively easy because it's just 2 steps, right? So at the end of the first year, you will have 1,070. Right? 1,000 times 1.07 equals 1,070. And then you add another 1,000 to your deposit. So at the beginning of year 2, you now have 2,070. You leave that on deposit for a year, and what do you have at the end of the second year? 2,070 times 1.07 equals $2,214.90. That's easy if you got just two periods, right? What if you're talking about 20 years, right? Or you're talking about quarterly payments over 20 years, which represents 80 periods, right? Then it becomes, you don't want to do that manually. You have a formula that you can use. Okay? So, suppose you need $1,000 in year 1 and 2,000 more in 2 years. Okay, if you can earn 7% on your money, how much do you put up today to exactly cover these amounts in the future? In other words, what is the present value of the 2 cash flows at 7%? So, what the present value of 2,007 years is 2,000 divided by 1,007. 1.07 raised to 2, which gives you 1,746. And the present value of $1,000 in 1 year, 1,000 divided by 1.07 gives you 934. If you add those two together, those two present values, you get 2,681. All right, now we can do a check to see, is that correct? That if I start with $2,681 today, I can take $1,000 out after year 1, and at the end of year 2, I'll have $2,000. Okay? So, we take that starting bit, the 2,681, multiplied by 1.07, so we know that at the end of year 1, we've now got $2,869. We take 1,000 out. What does that leave? That leaves $1,869. We earn 7% on that in year 2, and we get 2,000. So that gives us the 2,000 we needed in year 2. So that's just 2 periods, right? It becomes very cumbersome if you don't have a formula that you can use to calculate these amounts. All right, this is just 2 years. So imagine like a what do you call it? An annuity. An immediate annuity, right? So you retire, you get a lump sum, you go to an insurance company and you say, well, I need $3,000 a month for the next 10 years, 20 years until I die. The insurance company will do this calculation and say, well, can we pay them, how much do they need to put in today for us to pay them $3,000 a month for the rest of their life? All right, they'll make that calculation and they'll say, all right, you got to give us $632,000, 157, whatever today, and we'll commit to paying you $3,000 for the rest of your life. All right, they'll assume some really low rate of return, right? And their job is to not put their investors at risk, but at the same time, you want to know that you've got a steady cash flow for the rest of your life. Okay, and that's the benefit of an immediate annuity. A deferred annuity is where you're putting money in today, try to get to a lump sum in the future. Okay. So, you could say, well, I'm going to do a deferred annuity, lump sum every month until I retire. Then when I get that lump sum, I put it into an immediate annuity and get cash flows from the company. And the benefit of that is that, well, the negative is that lump sum is no longer yours. That's now the insurance company. That's the negative. The positive is that's no longer yours. The cash flows are yours. So, when Uncle Frank and Cousin Joe finds out you got a lump sum, guess who's coming knocking? I need to borrow $10,000 for this, and borrow that. Next thing you know, the lump sum you had just gets paid out. If you have an immediate annuity, you can tell them, hey, I don't have it. I can lend you 100, I can lend you 200, but I've got bills to pay, I've got my own things to worry about, here's my cash flow. So it takes away the risk of you spending or giving your retirement away. But the rate of return is really low, so bear that in mind. All right, so an alternative way of calculating present values for multiple future cash flows to discount back to the present one period at a time. For example, suppose we had an investment that's going to pay $1,000 at the end of every year for the next 5 years. To find the present value, you could discount each $1,000 at the end of every year for the next 5 years. Now this is what you do when you're pricing a bond. So like if you got a government or a corporation pays a bond, and you're trying to determine what the price should be, what you think the price should be today for those cash flows, really what's being done is each cash flow is being discounted back to the present. All right? So we'll go through this thing on the next page is a table we'll go through. So let's see. $1,000 for every year for the next 5 years, and the figure below illustrates on the next page the approach for a 10% discount rate. So this table on page 8, what we have here is really represents what a bond would look like. So year 0 times 0, I lend the government of the Bahamas $1,000. The government of the Bahamas is committed to paying me 10% per year for 5 years, and at the end of year 5, to give me my $1,000 back. Okay, so so this is slightly different. This is simply you get $1,000 a year for 5 years. Okay, and what would the present value be? And the rate of return is 10%. So at end of year one, we get 1,000. We discount it by 1.10. 1 plus t divided to the raised to the power of t. So 1 plus r raised to the power of t. So the interest rate is 10%. 1 plus 10% is 1.1. The time period is 1. Therefore, it's 1.1 raised to the power of 1. So why don't we do that in the table on the board? We'll work our way through it. You'll definitely have something like this on the test, I would imagine. So, I don't know, I don't write the test. But if I was writing a test and saw something, oh, that sounds like a good one. You know? Year 1, 2, 3, 4, 5. We want to know present value, right? What does present value equal? I need a marker word. Future value divided by 1 plus r t. Okay. So year 1, what's the future value? 1,000. Year 2, future value is 1,000. Year 3 is 1,000. Okay. And why do we do the discount factor, right? Remember that? 1 over 1 plus r t. All right. We know that r equals 10%, and t is 1 here in this case, and then year 2 is 2, 3, 4, and 5. So 1 divided by 1.10 raised to the power of 1 equals 1 over 1.10. Raised to the power of 2. 3, and so on. So why don't we calculate what these are? So 1 divided by 1.1 is 0.91.
Why divide by 1.1? Oh, the discount factor, sorry. Okay, go ahead.
So in the case of this year 1, the discount factor is 0.91. We can just multiply the 1,000 with future value by that. Right? Because what I've done is this here, the 1 over 1 plus r to the t, is a discount factor. So this is the present value. We take that times that equals
Ma'am, 909.09.
yeah. So 909.1.
No, I got what you got.
Yeah, I mean, if you, this is where I think it's in Excel when I did this table, so it automatically went up 2 decimal places.
Okay.
So, 1 divided by 1.1, this is that, times 1,000, equals 909.09. Okay. Let's do this, the second discount factor. This is for year 2. 1.1 raised to the power of 2 equals 1.21. You take the inverse, and you get 0.83. And multiply that by 1,000. You get 826.45. Raised to the power of 3 equals 1.33. Inverse 0.75. Times 1,000. Raise the power for 1.46, take the inverse, 0.68. Times 683.01. And you see the present value is going down each year, right? If you get a figure that goes up, you made a mistake, because it has to go down, right? Then 1.01, raise the power 5, equals 1.61, take the inverse, 0.62 times 1,000, 620.92. Why do we go through all of that? Because you want to know what you should pay today so that you can get $1,000 after year 1, after year 2, after year 3, after each year. You're paying for a total cash flow of $5,000, right? But you want to pay for it today. So you're trying to determine what the present value is. So you have to add up each of these 5 present value figures to determine how much you should pay today. So the total equals that, plus that, plus that, plus that, plus that. And we have the figure here, it's 3,790.79. Now we could go through the tedious process of checking this out, right? I could take this present value, multiply it by 10% for 1 year, I get a figure, take 1,000 out, take that figure and go for a year at 10%, take 1,000 out, and do that for 5 years in a row, and at the end of this, I should have nothing. At the end of year 5, the value should be 0. All right, so we did an earlier example with just, I think, 2 payments, right? At the end of year 1, I took 1,000 out. At the end of year 2, I needed 2,000. So let's suppose you're saying, I only need $1,000 a year for the next 5 years. And I find somebody that's willing to enter into this agreement where if I give them this amount today, they commit to giving me 1,000 at year 1, 1,000 year 2, 1,000 year 3, 1,000 year 4, 1,000 year 5. All right? If you had a bond, the difference would be at year 0, money would have left your pocket. You'd have made the investment. At the end of year 5, you'd have got, we're going to do a bond calculation, you'd have got the principal value back plus your interest. So this figure would have been a bigger number. Okay. So tedious, but I can see something maybe not for 5 years, maybe 2 years, 3 years being on a test, because it takes a long time. Right? You don't want to kill the student with too long a calculation. But all it is 5 present value calculations, right? And to determine the total amount that you've paid today, you can add those individual present values together.
Well, I'm sorry, what were you saying when you were saying you could take the money and then take 1,000 out each year? What figure were you talking about?
So if this is my present value,
Mm-hmm.
all right, so let's do, this is future value 1 year out. So future value equals 3,790.79 times 1.1. You're earning 10%. So at the end of year 1, what do I have? $4,169.87. Now what do I do? I take 1,000 out. Right? So now at the beginning of year 2, I don't have 4,169. I have 3,169.87. I multiply that by 1.1. Times 1.1. This equals 3,486.87. thousand by taking 1, 2, 3. So now we're dealing with U4, right? So 1.1. 1.1 equals 1909.09. You've seen that 909.09 before, right? Less my 1,000. I've got 909.09 left over at the end of year 4. Times 1.1 better equals 1,000 under the 1,000. That's my 5th 1,000. All right. So this is we're doing 5 present value calculations. This would be, and the key is to know what this figure is, right?
But that's what you would initially put in there.
Correct. That'll be your initial investment today, so you can get $1,000 a year for 5 years.
That's a particular rate.
At that particular rate. Of course, at a lower rate, this would have to be a bigger value, right? At a higher rate, it can be a lower value. Okay. So, you know, I mean, we're going to do a bond. You know, how do you price a bond? All right. You know, and we'll go through that. It's the same process, really, in effect, right? Pricing a bond is taking all the cash flows the bond has from now till maturity and discounting them back to determine what you should pay today. All right. Okay, so the example below is basically the same thing as we did in the table just above, only three periods. All right. So in this case, you've got an asset that promises to pay $1,000 each month for the next 3 years. The cash flows from this asset are in the form of a 3-year $1,000 annuity, right? And if you want to earn 15% of your money, how much would you offer for this annuity? 15%. Sounds like a loan shark or something, right? Well, you know, you take each cash flow and discount it back to the present value, right? And you see here, you get $2,283.22. Okay, it'd be nice if you could get that at 15%. But risk and return go hand in hand. There's no free lunch. All these sayings you hear, right? If somebody promises a very, very high rate of return, then you can rest assured there's a high rate of risk. Can I erase this? Remember now, emails there. Any questions? Like, what the hell is that? At least define that. Otherwise, don't imply the whole class was that, you know. So, very tedious, right? Fortunately, there's formulas out there that allow you to not have to go through all of those multiple steps. So let's look at this example at the bottom of page 8. So, you know, you go to the bank and you want to buy a car, right? So you need a car loan. And what they're going to try to determine is, well, how much can you afford to pay every month? Okay. So let's look through this example. So, a typical car loan calls for monthly payments over 3 or more years, right, for a total of at least 36 payments. All right. So in this case, since the cash flows on the annuity are all the same, we can come up with a very useful variation on the basic present value calculation. It turns out that the present value of an annuity of N dollars per period, the T periods, when the rate of return, or interest rate per periods R, is given by the annuity present value formula. Okay, that's not on these spreadsheets I gave you. So this would be kind of a new formula for you to learn. So in this case, N would be, what is that monthly payment? Okay. present value factor divided by R. Okay. What is the present value factor? 1 divided by 1 plus R to the T. So we plug that in. 1 minus. R. T. All kind of brackets, eh? Divided by R. I know, it gets nasty. Remember, always start from the inside of the bracket and work out. Okay? All right. Now, if we can calculate 1 over 1 plus R to the T, then we can plug that number in, right? Then it becomes not nearly as messy. All right. So let's do a practical example. So you're a loan officer and you're trying to determine the maximum amount that a prospective client can afford for a car loan. You have reviewed the prospect's budget and have determined that the maximum monthly payment possible is $500 per month. Okay? So we know N is 500. Okay? The going rate for a car loan is 12% per month, per annum, or 1% per month. Remember now, these are monthly payments, not annual payments. So what do we know so far? Let's plug it in. We know that N equals 500. We know that R equals 12% annually, right? So we're trying to determine what it is monthly. What do we do? 12 months in a year, take the annual rate divided by 12. I use 12% in this example because 12% divided by 12 is 1, right? Reality is usually a little messy than that. So, or 1% monthly. Okay, so the car loan is for 3 years, but it's a monthly payment. So how many periods do we have in 3 years? If we're dealing on a monthly basis? 36, right? So T, sorry, yeah, T equals 36. All right. So let's see, we got T, we got R, we got N. So now we can start plugging in. The first thing we want to do is calculate this messy bit here, right? We can do it over here on the side. So 1 divided by 1 plus R to the T equals 1 over 1.01. We're using this, right? Raised to the power of 36 equals, and this is, so 1.01. Turn it on, it works better with on. 1.01 raised to the power of 36 equals 1.43 inverse 0.7. Here we got 0.6989 in your notes. Okay, it just went up 4 decimals, so 0.7. We now know that this here is 0.7. And times 1 minus 0.7 divided by R. Okay. R is 0.01. We got to turn that percentage into a decimal. I know. But that's what we have to do. All right, so 1 minus 0.7 equals 0.3 divided by 0.01 equals 30. We know N is 500 times 30. I know we got slightly different, 15,055. That's because I didn't use 0.7, I used 0.6989. All right. So let's just walk through it again. So we start with this equation here, the annuity present value, or The lump sum I need, really trying to determine, remember I talked about the immediate annuity? If I wanted X number of cash flows for the next 36 months, what do I have to put in today? Well, the bank is looking like this. What do I lend today so I can earn these cash flows every month for 36 days? We've determined the cash flow is 500. That's the most the borrower can afford, right, to pay every month. And now I need to determine what's the maximum we can lend them. So first thing we do is that present value factor here, which is all messy. We calculate that on the side, so we can just plug that in here. Okay. Let me just walk through all the steps. So 500 times 0.3. All right. Divided by 0.01. Now, if you got multiplication and division, they're the same. You don't have to put brackets. Like I could take this divided by that multiplied by that. Or I could take that multiplied by that divided by that. I get the same result. All right. Let's just prove it. So 500 times 0.3 equals 150 divided by 0.01 equals 15,000. All right. But you can't do, you got addition, subtraction, multiplication, division, you can't, you need the brackets, all right? And if you got exponentials, you need the brackets, all right? Equals 15,000. So everybody in the bank, they got a computer, right? The bank offices, they plug it all in, right? And it spits out a result, all right? Well, when I first went to, I won't mention the bank, their calculation would have come up with a figure smaller than that. $500 a month, but the most I can lend you is $14,992. It wasn't big, but it's little, it was small. Okay. Flip it around, I can lend you $15,000, but your payment is not $500. Your payment is 552 cents. So 52 cents times 36. Adds up, right? Times 30 years times 12. What's that? 360. Starts adding up, right? Actually, more than that. Okay. 12 times 30. Yeah, 360. So little small increments over long periods of time, multiplied by multiple customers, starts to become big money. All right. Any questions on that one? I'm sure there are. The key thing, to take this nasty bit here, and to remember to do this, all right? You take this bit here, bring it over here and calculate it, and suddenly instead of this, you got that. Much easier to deal with that one. And I could have put 500 up here. We knew 500 from the get-go, right? Well, we couldn't do it up here because this is our formula. But at this point, as soon as I do it, I could have plugged it in. All right.
This is you working on the monthly one.
This is determining how much I could borrow.
At 1%? Or don't matter?
I know you can afford. I know you can afford a payment of $500 a month, right? And we're going to do it over 3 years or 36 months. How much can I lend you? That's what I'm trying to determine as a banker. How much can I lend you?
Oh, so that's 12% annually and 1% monthly.
Monthly.
I don't think that sounds good. Where does that come into here?
Well, because the payments are on a monthly basis, not an annual basis, we need to convert the annual rate to a monthly rate.
So you're charging 1% monthly, but you turned it
Yeah, I mean,
in annual.
well, we had the 12% per annum, and we had to convert it into
1%
monthly.
a month.
Yeah.
Okay.
So if it was a quarterly payment, it would be 12 divided by 4, or 3%. If it was a semi-annual payment, 12 divided by 2, or 6%. And then T is the number of periods, right? Not number of years. And because we're paying on a monthly basis, 3 years becomes 36 payments, or 36 periods.
So it's quarterly, then it would have been different.
If it was quarterly, there's 4 periods per year, it's 12.
So you get the same answer if you had the rate is 12% and the time is 3?
You get a different answer because of the impact of compounding.
How much of a difference?
I don't know, let's find out. Well, let's think it through now. So I think this figure will be a little
1.1
smaller.
To the
So
third.
I think we can borrow a little bit more, but let's find out. So what was your question? It was annual, right?
Right.
Okay. So this figure here is going to be 1.12 raised to the power of 3. Take the inverse. 0.71. Right? 0.71. 0.29.
Why do you say we do this, the inverse again?
The 1 over x button.
You just press it once you get your answer.
Yeah, so if you had your the 1 plus r raised to the power t, you get that figure. And then you hit the inverse button, and it does the calculation of 1 divided by that for you. So what do you get? 14,500? Oh, wait, no.
Yeah.
Oh. Ah,
He's gonna know 1% money, right?
n is no longer 500.
Right.
It's got to be 1,000 more. See what I'm saying? So your total payments are the same. But from a bank standpoint,
This is for a loan?
this is a loan.
Mm-hmm.
So you borrow,
Sorry, so, the 500 and 6,000. N and C is the same thing then?
well, because we're looking at an annual example, right? We're trying to determine, you're only making a payment once every year.
So, the 500 is the once every year?
500 is every month. So I've determined you can afford 500 per month
Mm-hmm.
or 6,000 per year.
Mm.
All right, so you can, if you make a payment of 6,000 once a year for 3 years, how much can you borrow? Remember now,
Okay.
interest is based on the principal outstanding. Every time you make a monthly payment, a part of that goes to principal. So you're paying down the principal faster than you're paying monthly. Therefore, I'm going to lend you more today. You can, if we did, so 15,000 what you can borrow if you're paying off monthly, but I'm only going to lend you 14,500 if we're paying off annually. Right?
But how come?
There's more risk to the bank now. I don't get any of the principal repaid until the end of the year. Whereas monthly, you're repaying principal a little bit every month. So my exposure to you, my risk to you is actually less if you're paying off monthly.
Instead of waiting out the whole 12 months.
Right, and I'm willing to lend you more because in effect the risk is lower now. All right. That was interesting. No one's asked that question before. It's kind of fun to do it. And I never really thought of that. If the payment period gets longer, then the bank in effect is willing to pay less. Because don't forget, this figure is fixed. Eh? Like how much I've determined you can afford to pay is fixed. That doesn't move. 500 a month or 6,000 a year.
And then the percentage would be, you have anything they show at you 16%,
Well, I
9%.
mean, yeah, so obviously if the interest rate is not 12, but it's less than that, I can borrow more. Right? Because every month more my payment goes to principal. So
But it could be 9% annually.
let's just see. So if it was 6% per annum, 1.06 raised to the power of 3, take the inverse, 0.84.
it down to 3.
I'm just trying to do the same annual,
Oh, 3 years.
yeah,
Okay,
3
cool.
years. No, sorry,
The 3 years, you still have to do,
let's do it, we do it monthly. So 6% is an annual rate, a monthly rate is 0.5%. 6 divided by 12. All right.
do that?
If the annual rate was 6%,
Uh-huh.
the monthly rate would be 0.5%.
Mm-hmm.
6 divided by 12.
Mhm.
So if it was 0.5% and we plug it in here, we get 1.005 raised to the power of 36 inverse 0.84. So now we take the 0.84 and plug it in here. 1 minus 0.84. 1 minus 0.16 divided by 0.005 equals 32 times 500 equals 16,000. Which makes sense. I got like 84,000 first time I did it. I was like, what? I did something wrong. But that makes sense, right? Because if the rate of interest is less, I can borrow more. Because every month, more and more of my payment is going to principal.
The higher the interest, the more voice the interest.
Just don't forget the payment's fixed, right? That doesn't change. That 500, that's the most you can afford. The lower the rate of interest, the more I can lend you. The higher the rate of interest, the less I can lend you. Because a portion of that 500 every month goes to interest and principal. The lower the rate of interest, the more of it goes to principal. And therefore, the faster you're paying off principal, the more it can lend you up front. If the interest rate was higher than the amount it can lend you, it would go down, right? Alrighty. You definitely have something like that. That's not, right there, right? Your loan officer is trying to determine how much you can, the maximum amount that a second client can afford on a car loan. You reviewed the blah, 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 right? That, oh, okay. And you need to know this formula. You're given the variables, you gotta plug it in and calculate. I mean, that's a very, very reasonable expectation that that would be on your exam. Find in the payment. Remember I said this is the only real mathematical part of the session, right? Next 2 weeks, we talk about investment products, and we talk about investment management, investment policy statements, life cycle, investment life cycle, investment strategies. This is really the only mathematical bit. There are a couple graphs looking at options, call options, and put options, and strikes, and that kind of stuff. So once you get through this bit tonight, you can go, thank goodness. Once you have to review it. All right, so find the payment. Suppose you wish to start a new business that specializes in the latest of health trends, push T. I think when I first wrote this question, somebody in my office was selling gallons of bush medicine. I was like, man, it's all natural, you know. It's good for you. I said, well, cobra venom's all natural, I killed you. What is the correct dosage? You know, a gallon? A thimble full? What's the appropriate dosage, you know? And actually, a friend of mine is a doctor, he says that's a big problem. A lot of people, you know, bush medicine, they think it's good, but they're actually doing all kinds of damage to their kidneys and liver because it's just too much of a good thing. You could die from too much water. And you've heard that story of the lady who had that, some radio in Chicago, they had a challenge how much water she could drink in an hour. She died. She diluted her bloodstream to such an extent she died. Her body lost its ability to transport oxygen, so you can die from too much water. Alrighty, what are we doing here? Island blend. This has been tested and we've determined the appropriate amount. It's all on the label. Alright. But it is a trademark, a secret recipe. You can't reveal that. All right, you need to borrow $50,000 at an interest rate of 15%, and for 5 years, okay? Yeah, so you know, you're saying, okay, I need to borrow $50,000, and the interest rate is 15%, and we're looking at a 5-year time frame. The payments are all equal, so you need to find the relevant annuity factor to solve the unknown cash flow. Okay, so in this case, we're solving for n. The last time we had n, right? We were trying to. Last time we were trying to solve for the 50, and you know, 15, right? In this case, we know that 50 is how much we need to borrow. We know the rate of interest is 15%. We know the time is 5 years, okay? And in this case, we're making annual payments. So the question is, what do those payments need to be? So you flip roles, right? Last time we were looking at it more from the lender standpoint. In this case, we're looking at it from the borrower standpoint. So we got our calculation up here. Need more space. Let's roll it over. What do we know? We know the annuity present value. And that's the unknown. R is 15%, and T equals 5. So we made it simple. It's just annual payments, not monthly, not quarterly. Okay. So we have all of that in info. All right. So 50,000 equals n times 1 minus the present value factor divided by r. So why do we get n all by itself? Well, you know what? Let's do what I said before. Let's do the present value factor calculation. So we come over here, we've got the present value factor equals 1 over 1 plus r to the t equals 1 over 1.15 raised to the power of 5, right? So 15% of 5. All right. 1.15 raised to the power of 5. 2.01. Take the inverse. 0.5 equals 0.50. We now plug that in. So 50,000 equals n times 1 minus 0.5 raised to, and we know what r is, right? Divided by r. R is 15 divided by 0.15. R is 15%. So divided by 0.15. Now why don't we just do this calculation here while we're working at it, right? And this is time, right? So we got 1 minus 0.5 equals 0.5 divided by 0.15 equals 3.33. So 50,000 equals n times 3.33. We divide both sides by 3.33 to solve for n, right? N times that equals 50,000. So if I divide both sides by 3.3, these cancel out, and we're left with n, well, 50,000 divided by 3.33 equals n, or just flip it around, right? N equals 50,000 divided by 3.33, which equals 15,000. What do we get? Some rounding impact there, right?
Yeah, that's 0.49.
Yeah, so here we have 0.4972 instead of 0.5. Okay? And we had 3.352 instead of 3.33. All right, the rounding impact. I went up 4 decimals here. I imagine that maybe I should go up 2 decimals. most calculators are set at 2 decimals. Right? So, you know, I'm a loan shark, and you're desperate to get your business going. All right, I'll lend you 50 grand. You got to pay me 15,000 a year for the next 5 years. And guess what? If you miss a payment, decap. All right, but you know, 15,
How
50.
much? Yeah.
Yeah,
For
5
5
years.
years?
Yeah, so total payments of 75,000, so you can borrow 50 today. But credit cards are 18%. This is cheap.
Yeah.
This is a high. This is like a high net worth client's credit card. It's a special client's credit card, right? You know? But you know, if you're starting up a business, actually 15% is low. Brand new business, out of the gate, all the risk. You really know how you know how to run a business? You know how to market your product? Are you really driven? Are you entrepreneurial? I don't know. You know, I'm taking a lot of risk lending this money. And to compensate for the risk, I need a high rate of return. So actually 15% for a startup is actually low. And everybody's, oh, you know, I don't like lending money for startups. Startups are risky. Like 9 out of 10 startups fail. Right? So that means 9 out of 10 times I lend you money to do this, I don't get my money back. You know? So that's why it's difficult to find. And we're a very risk-averse investing community. We don't like risk. Whereas in the U.S. and other places, you know, people are willing to take a lot more risk. So like venture capital firms, they understand 9 out of 10 are going to fail, but it's the 1 out of those 10 that makes it. You know, they have equity in it, and they expect to make big returns to compensate for all the losses, right? So I remember one time we had a company, and ironically it was a beverage company. They're looking to raise money. It was a startup. And we projected a rate of return of 35%, you know, on this investment. If all of these assumptions happen, you know. And one of the potential investors goes, is that guaranteed? Really? And you know, unfortunately, a lot of our successful business people have, I think, made money because it's kind of like a oligopolistic, monopolistic environment, right? It's like you can make money despite yourself back in the day. So, all right. What's next? Future value for annuities. So this is more like the deferred annuity, right? How much, if I put an X amount per month or on a periodic basis over a period of time, how much can I expect to have at the end? Okay? And remember now, in this case, let's see, you're doing 5,000, 4,000 per year over 30 years at 7%. What will that be worth at the end of the 30 years? You can go 4,000 times 1.07 raised to the 30, 4,000 times 1.07 raised to 29, and do that. 30 separate future value calculations, and then add them up. In Excel, actually, it's not that difficult, right? Because once you set it up right, just copy 30 times, and then have a sum at the bottom, and it adds it up for you. But even that is still somewhat tedious. It'd be nice if I could have a formula where I plug in the 4,000, plug in the 30, plug in the rate, and it spits out the result. Those spreadsheets, the spreadsheets that I gave you, are you leaving us? All right.
I don't know how choice anymore.
See you later.
Okay.
These spreadsheets I gave you, right? A lot of these things are plugged in like that, right? So, for example, you know, 4%, 5%, 6% over 25 years. If I started with 0, but I wanted $1 million, how much would I have to invest every month to get to that? And you see this kind of tables, right? And $1 million. I don't know if you're looking at the one that has 0 initial. You see down the annuity present value, you know, different ranges, but the million is closest to kind of like 1.028. And of course, you can tweak this, right, until you get the number you want. And that relates to $2,000 per month at 4%. Because, you know, this table here, if you go down, they follow each other. Or you could do $1,500 a month at 6%. $1.039 million down at the bottom right. So here's a way you can plug in assumptions and come up with a realistic determination of what needs to be done. So if you're risk averse and you want an investment that's only going to give 4%, well, guess what? You got to put $2,000 in a month to get $1 million in 25 years. If you're willing to take a little more risk and you look for something that earns 6%, you only need $1,500 a month. Granted, this makes assumptions that it'll be that steady 6% every year, no fluctuation in rate of return. These are all grand assumptions, right? That's why I like the idea of a table, and you can tell somebody, well, you know, assuming you can get 5%, assuming it doesn't fluctuate, you need to put in X amount, approximately X amount to get to this figure. But if you really want to be certain, you probably need to add more. And that way you compensate for some of this uncertainty. There's nothing, if somebody comes in and says, like an annuity, I want $1 million in 25 years, what do I have to give you every month to get there? Guess what I'm going to do? Well, you give me $3,000 a month, and I guarantee you get your $1 million. Turns out to be like a 2%, whatever, 2.5% rate of return, because I know I can go ahead and earn 5%, 6%, and earn the spread on it, right? So, I can promise you $1 million, but here's what you got to pay me every month. Your rate of return is going to be low, because I'm not, I'm taking risk. I'm guaranteeing this $1 million, right? So, all right, let's look at this calculation down here. So, in those spreadsheets I gave you, this calculation on your material is what's built into this spreadsheet. What I told Miguel is, I'll send it to him, and you guys can just have it. I just created it myself, so I think it's useful, for your own benefit, but also if you're in the business, this question comes up all the time. First question, how much can you afford every month? All right, I can afford $1,000 a month. Well, how risk averse are you? There's the ability to take. We're talking about this in the class 3. The ability to take risk and the willingness to take risk. They're not necessarily the same. If you're younger, your ability to take risk is greater because you've got more years ahead of you. As you get closer to retirement, your ability to take risk gets less and less and less because you've got fewer years. Something, if your investment if your investment drops in value and you're 25, you still got 40 years to recover. If you're 50, you got 15 years to recover, assuming 65. If you're 60, you got 5 years to recover. So your ability to take risk gets less and less as you get older, or closer to your objective. Then there's the willingness to take risk, right? So I mean, some people, if the investment ever goes down in value, they're like, they're losing their mind, right? They're very risk averse. They're not willing to take risk. But if short-term fluctuations don't bother you and you're really focused on the long-term, growth, then you're less risk averse and more willing to take risk. Okay? Gamblers, very high risk takers, right? They may not think it, but if you buy a lottery ticket and the options offer what is it? 14 million, whatever the odds are, right? Yeah. Then you just do it to say you're having fun. If I buy a lottery ticket when I go across, it's like, wouldn't this be funny? I was sitting in a restaurant as a university, right? And we bought some. This is in Florida, so we bought the lottery ticket. We were looking at, we got 1 out of 6 numbers, right? The guy at the table next to us goes, "What's the numbers?" We called the first one. We go, "I got that." Called the second one. "I got that." Third one. "Oh, good." Fourth one. "Oh, I got that." Fifth one. "Yeah, I got that." We just like, no way. Called the sixth one. He goes, didn't have that.
Still want some
We
money.
didn't believe him. We went on the table and looked. The dude had the first 5.
Yeah, still want some money.
He got $5 grand. He didn't get 50 grand. But he was so calm about it. Like, almost like he'd done it before. If that was me, I'd have been all
Jump in.
You check it.
All right. So let's see. On this occasion, what do we have? We have an example where you plan to contribute $4,000 every year into an individual retirement account, paying 7%. If you retire in 30 years, how much will you have? Okay. So the annuity present value equation comes into play again. what do we have? This is what we don't know. This is 4,000. How many years? 30?
Yeah.
And 7%. Okay. The first thing we're going to do is equals 4,000 times minus the present value factor. Oops. Divided by R. Let's go over here and do this calculation. Equals 1.07 raised to the power of 30, right? Okay. So, 1.07 raised to the power of 30 equals 7.61. Hit your inverse button, 0.13. Equals 0.13. That goes in here. 1 minus 0.13 divided by R is 7%, or 0.07 as a decimal. Alrighty, 1 minus 0.13 equals 0.87 divided by 0.07 equals 12.43. Let's write that in. 12.43 times 4,000. Is that right? Oh, okay. Yeah, so that, sorry. You got to do the present value, and then you got to turn that into a future value. All right, so this is the present value of these cash flows, 49,000. 714.29. So there's a two steps to it. First of all, we have to determine what is the present value of all these cash flows, right? Which we've just done. So the present value of all these cash flows is 49,714.29. So this is our annuity present value. Now we need to determine what is that figure, that lump sum, what is its future value going out 30 years. In your notes, where it says future value equals 49,634.29 times 1.730. Typo, that 30 should be an exponential. 1.07 raised to the 30. Okay, I thought I got all the typos, but I missed that one.
Where's that, sorry?
At the bottom of page 9,
Okay.
see what goes future value equals 49,634.29 times 1.70730.
Mm-hmm.
That 30 should be an exponential.
Oh.
That should be 30. So just put a line through it and then put 30 up above,
Right.
upper right of the 7. All right. So the future value equals present value times 1 plus R to the T, right? Equals 49,714.29 times 1.07 raised to the power of 30. 1.07 raised to the power of 30 equals 7.61 times 49,714.29. 378,437. Why is it a little bit different?
Did you round it?
Yeah. Alrighty. So what that does is it shows you, you know, if you can afford to invest $4,000 a year for 30 years at 7%, what will it be worth at the end of the 30-year period? Okay. And it's two steps. So you got your cash flow, you got your rate, you got your period. You need to determine the present value of those cash flows, or the annuity present value, and then convert that present value into a future value. It's a little tricky. On page 10, we look at the effective annual rate. All right, so if I can put an investment and earn for a year and earn 10%, or 12, to use 12%, or I can earn 1% per month, right? Which is the higher effective rate of return? So 12% is an annual rate, so I can earn 12% on 1,000. At the end of the year, I've got $120 of interest. 1,000 plus 120. 1,000 times 12% is 120. Or I can earn 1% per month. And each month, that 1% compounds. So I'm earning interest on my interest every month. At the end of the year, I'll have more than $1,120. I'll probably have $1,121 or something like that. Well, why don't we do that? Let me see what it is. I'll let you know. 1.01 raised to the power of 12 equals 1.3. Yeah, so $1,126.83. All right. So what is my effective annual rate of return then? It's not 12. It's 12.68%. But let's do an example. All right. So quite often the quoted annual rate and the effective annual rate are not the same. For example, if a rate is quoted as 10% compounded quarterly, then the investment actually pays 2.5% every 3 months. Earlier we asked whether 2.5% per quarter is the same as 10% per annum. Did we? Anyway, maybe we didn't read it, but it was in the notes. Well, let's find out, right? In scenario 1, we invest 1,000 at 10% per year. At the end of the year, we have $1,100, right? In scenario 2, we invest 1,000 at 10% compounded quarterly. Now, so therefore, we've got 4 periods per year. We take the annual rate of 10% divided by 4. That becomes 2.5%. And T is now 4, because we have 4 periods, right? So the future value is 1,000 times 1.025 raised to the power of 4, which equals 1.1038. So we end up with $1,103.81. So in scenario 2, we earned an extra $3.81 of interest. Therefore, the effective annual rate of return is 10.381%. So how would we, what's one way to calculate that 10.381%? Let me show you a useful little calculator. So, annual rate. So let's suppose that my present value equals 1,000, and I know that at the end of the year my future value equals 1,100. 380, is that what that said? 1,103.81. How can I determine what the rate of return was? Let me show you. Take your future value, divide by the present value, and then subtract 1. So if I take 1,103.81 divided by 1,000, what we did. But it was 1.1038, and I subtract 1, and I get 0.1038. decimal, you turn that into a percent, move the decimal 2 places to the right, or multiply by 100, and you get 10.38%. All right, so in Excel is really useful, right? Take the ending value divided by the beginning value and subtract 1, and there's your percent change. Okay? That's just a little trick of the trade. So what is the formula for the effective annual rate? Let's do that. One plus quoted rate divided by n. Divided by n. Minus 1. And let's do the example we just did. So 1 plus 0, which is 10%, 0.10 divided by 4 times. Oh yeah, minus 1. Okay. All right. Equals 1.025 minus 4 minus 1. Okay. Makes sense. I have a feeling we got into the exponential again. I believe that this n would be here. It should be minus 1. Let's see how that works. That makes a lot of sense. Otherwise, how do we have any compounding, right? So I think it's a typo in the middle. Let's see. 1.025 raised to the power 4 minus 1. 10.38. Okay, so in your notes, in that effective annual rate of return equation, you got bracket 1 plus open bracket 1 plus open bracket quoted rate close bracket divided by n close bracket. The next n should be an exponential. All right. Then all of that. Once you've done that, subtract 1. So the same little trick I showed you. The same idea. N should be up here as an exponential. Okay. All right. And this, just to write it out, this equals 1.1038 minus 1 equals 0.1038, which equals 10.38%. All right. So here's a question for you. I want you guys to work this one out. All right. Don't worry, almost done. Almost done. Probably like 8 So here's the question, you've got 3 investment options, right? All right. There are 3 investments and all require the investment to invest $1,000 for 5 years. But the interest rate and the compounding period differ. Investment 1, 12% compounded monthly. Investment 2, 12.4% compounded quarterly. Investment 3, 12.8% compounded annually. So the question is, which is the best investment? So you have to determine the effective annual rate in each case. Well, the compounded annual is pretty easy, right? So the effective annual rate of return is 12.8%. Now we know that the 12% compounded monthly, the effective annual rate of return will be more than 12, and the 12.4 compounded quarterly will also be more than 12. But will either one of those be more than 12.8 is the question. So how do we do it? You got your effective annual rate of return equation, and let's look at investment 1. So what is the quoted rate? So just 12% compound monthly, right? Now these are all annual rates, but they compound monthly or they compound quarterly. All right, and N is the number of times the interest is compounded. So interest compounds 12 times, right? So effective annual rate equals 1 plus 0.12 divided by 12. No, I'm sorry. Because it's for 5 years, you have to do it for everyone. I believe. I'll do it with you. Divided by 12 raised to the power of 12 minus 1. Yeah, I'm just looking, really what we're doing here, I don't know, it's actually not the effective annual rate of return. We're just trying to determine which investment is the best option. All right, so you're simply, it's a future value. So the present value is 1,000, and it's investment 1, you're earning 12% of compounded monthly. So what do? You have to convert that 12% to a monthly rate. And then the number of periods has to be 5 years times 12 or 60. And then you determine what the future value is. So it's not an effective rate of return. Effective annual rate of return when you're looking at a 5-year time frame doesn't make sense. And of course, quarterly, you take the annual rate divided by 4. It's 4 periods per year, 5 years. Exponential is 20, right? So T is 20. Investment 3 is just 5 years, so T is 5. Anybody ever watch that series back in the day called Seinfeld? And there was this George, one of the characters, right? He was about to get married, then he wasn't sure he wanted to get married. And his fiancée was doing wedding envelopes, and she was licking them all. And she poisoned herself and died. He was actually kind of relieved because he didn't want to get married.
Oh my God.
I'm just hoping that this, me erasing the board with my fingers isn't like that, you know. Especially if I started. How are we doing?
I'm getting pretty,
Let's do the first one. It's really the most complicated of the three, just because it's monthly, right? So it's 12% annually or 1% monthly, and it's for 5 years. So 5 times 12 is 12 compounding per year, right? So the total number of periods is 60. All right. Now the key is, if you forget to convert your interest rate to a monthly rate, and then you do it to the power of 60, you're going to get a huge number. That may be it. And you know, and that's always a definite sign that something's wrong, right? You made a mistake along the way. You got a really, really big number. So 1.01 raised to the power of 60 equals 1.82 times 1,000 is 1,816.70. So if you do the first one right, then the next two got to be somewhat close to that. Then what you could do is do the simplest one first, right? And get an idea. So like the one below the annual rate of return. So 1.128 raised to the power of 5 is 1.83 times 1,000 is 1,826.19. So now you know the results of the other two have to be somewhere close to that, right? If you get some incredibly different number, then you know you made a mistake. So we now know that investment 3 is better than investment 1. So you end up with a higher future value. 1.031 raised to the power of 4. Divided by 4 equals 0.31. Okay. 1.031 raised to the power of 4 equals 1.4. Not raised to the power of 4, dummy. 20. All right, I got 20 over here. Wait a couple little Susie. 1.31. That's Jim Carrey. 1.84 times 1,000. 1,841.51. So obviously that's the best alternative, right? And you end up with a higher value. That could be a question. 3 future value. I mean, that captures a whole bunch of stuff, right? Converting an annual rate to a monthly rate. Converting the periods to monthly in terms of the number of periods. Quarterly rate, annual rate to quarterly. Right? Being able to do the calculation. All right. So I would say with absolute certainty you need to be able to do something like that. I mean, I don't know, but that's a good one. That captures a lot of little bits and pieces all in one question. Right? I can flip it around and say, which is the, no, never mind, that wasn't it. They'd all end up back to 1,000. Never mind. But you could do a present value scenario, right? Scenario 1, 2, 3, which has the highest present value? And you have to do the 3 present value factors. All right, so on page 11, you see the calculations we did on the board, right? They're in the material. Okay. And yes, 20 is in the exponential. Thank goodness, not 4. Okay. And really, let's see, three types: a pure discount loan, interest-only loan, and amortized loan. So pure discount loans are the simplest form. So with such a loan, the borrower receives money today and repays a single lump sum at some time in the future. Those T-bills we talked about are an example of that, right? So the borrower gets a discount, $900,000 today, and agrees to pay $1 million in a year, something like that. Okay, so that's a pure discount loan. So let's see. With such a loan, the borrower receives money today and repays a lump sum sometime in the future. Such loans are usually short-term in nature. For example, 1 year. A 1 year, 8% pure discount loan will require the borrower to repay $1.08 in 1 year for every dollar borrowed today. All right. I lend you $1 today, you give me $108. $1.08, sorry, at the end of the year. Common examples of pure discount loans are treasury bills. All right. T-bills, as they're called, have terms of 90, 180, 270, or 360 days. A T-bill is a promise by a government to repay a fixed amount at a specified date in the future. The future value is fixed, and the present value is calculated based on the discount rate or yield to maturity. In this example, assuming the 360-day T-bill, the maturity value is $1 million. The yield of maturity is 4%, so that would be your discount rate. What is the present value? $1 million divided by 1.04. Number T is 1, so there's no need to worry with exponential. Equals $961,583. So I would lend the government $961,000 today, and a year from now they repay. They give me $1 million. Example we talked about here. So, common example of an interest-only loan is a bond. The issuer promises to pay the lender interest over the life of the bond, and then repay the full principal and last interest payment at maturity. So, 10-year bond, like the government is issuing bonds starting Monday. They got one bond that matures in 2038, so that'll be 20 years. The rate of interest is 5.06% fixed. So if you gave them $100,000, right, you invested, each year you would get $5,060 in interest. And they do it in semi-annual payments. So you get half of that in 6 months, the other half of that in 6 months. So each 6 months you'll be getting an interest payment of $2,530, right? And that'll go for 20 years. 20 years out, at the very last payment, not only will they give you the $2,530, they give you your $100,000 back, all right, in one lump sum. All right. Whereas the last loan we talked about is an amortized loan, and that's where each payment is a combination of interest and principal. And most of the loans we're used to dealing with in banks are amortized loans, right? So you're paying a combination of interest and principal in the payment. Okay. That's pretty much it for today. Is that okay? That's a tongue-in-cheek clap, right? You agree. See you later. All right. Remember, any questions, feel free to email me, all right? A lot of math in one night. The next 2 nights won't have this math. Talk about investment products next week.
And you said you're going to send Excel?
I'll give that to Miguel, and you can give
Miguel,
it
and
to
you email it up?
Yeah.
Okay, great.
It's just one spreadsheet, and you can just change it as you will.
You're going to work out the LN factor?
Yes. Yes, sir. We'll just do that quickly on next week.
Pleasant good evening, folks.
All right, man. Take it easy. Those people online, late. Just so you know, making some edits to the material that's been given to you. When I say edits, just some edit with some, maybe some few issues that need to be updated or corrected. And we'll make sure you have those before each class. Sometimes you have issues with loss in translation, you know, like you email a document and then it gets reformatted and put into the format, things get skewed and changed. So I need to go through it and make sure it's correct. Swim, bowl, DS.
Oh, yeah.
I like to swim, I like to bowl, and I just get the use. On the internet,
Yeah.
and ask like, you know, future value calculations, present value calculations.
Oh,
Hello?
email address.
Oh, sure. Swim, SWIM, BOWL, D as in David, S as in Slaughter, @gmail.com. You're welcome. Take care.